Welcome to The Explainer. For week one of our deep dive into the foundations of modern science, we're looking at the breakdown of classical physics, black-body radiation, the photoelectric effect, and the messy, mind-bending birth of quantum mechanics. You see, progress isn't always some smooth, logical march forward. Right at the dawn of the 20th century, physicists literally had to abandon their entire grip on reality just to make sense of some stubbornly impossible data.
Okay, let's dive right into this totally bizarre problem that completely broke 19th century science. It was known as the ultraviolet catastrophe. It started with a pretty simple question about glowing objects. But when physicists applied their absolute best, most rigorously tested theories to it, the math confidently predicted that the walls of the very room you're sitting in right now should be drenching you in an endless, lethal torrent of ultraviolet light. Now, obviously, you aren't currently being vaporized. But the fact that respectable physics predicted something so profoundly absurd meant that something at the very foundation of reality was badly, badly broken.
So to understand why the math broke down so spectacularly, we have to look at how objects actually glow. As everyday things get hotter, think of a blacksmith's iron in a forge, their glow shifts predictably. It goes from a dull red to a bright orange and eventually to a dazzling yellow-white. And it doesn't even matter if the object is iron or a lump of coal. The glow basically acts as a universal thermometer. As the temperature rises, the peak of that glowing light naturally shifts toward the higher frequency blue end of the spectrum. This is called Wien's displacement law. It was exactly the kind of universal, reliable fact that classical physics really should have been able to explain.
But classical physics spectacularly failed to explain that simple curve. The classical prediction, known as the Rayleigh-Jeans law, assumed that energy was this continuous, smooth fluid that could be divided up into arbitrarily small amounts among all the different electromagnetic wave modes in a cavity. Because there are endlessly more ways to fit tiny, high-frequency waves into a confined box, the classical prediction just shoots straight up to infinity. But nature, thankfully, outright refuses to do that. The actual observed data safely rounds off and drops right back down in the ultraviolet range, completely ignoring those classical rules.
Just to put into perspective how completely off the classical model was, let's look at the numbers. If you take a hot object at 3000 Kelvin and measure just one specific ultraviolet frequency, the classical equations overpredicted the actual energy by a factor of 50 billion billion. That's a 5 with 19 zeros behind it. This wasn't just a tiny rounding error, guys. It was fundamentally, catastrophically wrong.
Section 1. Planck's desperate remedy.
To fix this massive absurdity in the year 1900, physicist Max Planck proposed what was basically a radical, desperate mathematical patch. He stubbornly wanted his equation to fit that curve, so he just abandoned the long-held idea of energy acting as a smooth, infinitely divisible fluid. Instead, he proposed that the tiny electric oscillators in the walls of a glowing object could only trade energy in discrete, fixed chunks. He called these chunks quanta. Think of it like a currency that only comes in whole coins, rather than a liquid you can divide down to the very last drop.
And the crazy part? By forcing energy into these discrete steps, the math finally worked. At low frequencies, the steps are so tiny they essentially feel like a smooth ramp, acting just like the classical fluid. But at high, ultraviolet frequencies, a single step is massive. A glowing wall simply doesn't have enough ambient heat to boost an oscillator onto even the very first rung of that ladder. Because that first step is just too high, those high-frequency modes stay completely dark. The infinite energy pileup is throttled, and the catastrophe is officially cured.
Moving right along to Section 2, the photoelectric puzzle. Of course, patching one hole in physics just revealed another one. Over in Heinrich Hertz's lab, a completely different experiment was actively breaking the wave theory of light all over again. Hertz noticed that shining ultraviolet light on a metal surface caused it to spit out electrons. Now, if light was really just a continuous wave, like water slowly filling a basin, it should eventually wash enough energy into the metal to shake an electron loose, no matter what color the light was. But experiments showed three absolutely impossible facts. First, there was a hard threshold frequency. Below a certain color, no electrons came out, ever. Second, the energy of the escaping electrons depended entirely on the light's frequency, not how bright it was. And third, emission happened instantly. Zero delay. No time for any sort of wave energy to build up.
Which brings us to Section 3, Einstein's particle of light.
Fast forward to 1905, and Albert Einstein takes Planck's abstract math and makes an incredibly bold claim. Planck had only said that matter traded energy in chunks, but Einstein declared that light itself is not a continuous wave at all. He argued it's actually a hail of individual, indivisible particles, which we now call photons. This idea perfectly balances the energy budget. A single photon acts entirely alone, handing over its complete energy payload to a single electron in a flash. To escape the metal, the electron has to pay an energy toll, known as the work function. If the photon brings more energy than that toll, the electron escapes and keeps whatever is left over as the kinetic energy of its own motion.
This beautifully explains that mysterious threshold we just talked about. If the incoming photon's frequency is too low, its energy packet is just too small to pay the toll. It literally doesn't matter if you shine a blinding 10,000-watt lamp on the metal. That just means you're firing millions of faint photons, but since each one acts completely individually, none of them can clear the barrier alone. It's a wall that brightness simply cannot climb.
Now, the idea of light as particles was so radical that prominent physicists outright refused to believe it. Robert Millikan spent years making incredibly precise measurements in a vacuum, fully intending to disprove Einstein's absurd particle theory once and for all. But instead, his data ended up matching Einstein's equations perfectly across multiple different metals. Millikan published his results in 1916, famously and begrudgingly admitting they were obtained in spite of his personal conviction. In a beautiful twist of irony, he eventually won a Nobel Prize for exactly the measurements that proved the theory he hated.
Any lingering doubts about light acting as a particle were totally crushed by 1923. Arthur Compton fired X-rays at electrons and just watched them scatter. The X-rays bounced off the electrons exactly like billiard balls colliding on a table, transferring momentum and shifting to a longer wavelength in the process. Classical wave theory predicted no change in wavelength whatsoever, so this definitively proved that light particles carry real physical momentum, completely sealing the fate of the classical wave-only model of light.
All right, our final section, the quantum scale. So, the universe, it seemed, had this profound symmetry. This duality led a young physicist named Louis de Broglie to ask a genuinely wild question. If light can act like solid matter, what if solid matter acts like a wave? In 1924, he assigned a literal wavelength to all matter, stating that a particle's wavelength is inversely proportional to its momentum, and this bizarre theory was brilliantly and totally accidentally confirmed at Bell Labs. After a glass vacuum flask shattered and oxidized a nickel target, scientists had to heat it up to clean it. This fused the nickel into large crystals. When they fired point-like electrons at it, the electrons diffracted off the regularly spaced rows of atoms, creating an interference pattern just like ripples in a pond. Matter itself was waving.
Now I know what you're wondering. If matter is a wave, why don't you see people diffracting when they walk through a doorway? Well, quantum mechanics isn't just for tiny things. It governs large objects too. But you have to look at the scale involved. A 54-electron-volt electron has a wavelength comparable to the spacing between atoms. A 70-kilogram human walking at a normal pace has a wavelength of 10 to the power of negative 35 meters. That is 20 orders of magnitude smaller than a single proton. The waves are there, sure, but they are practically non-existent on our macro scale.
And this brings us to a really mind-bending conclusion. You are entirely built of localized particles that are fundamentally governed by wave equations. Max Born later proved these aren't physical waves in space, like water, but waves of pure probability that dictate where a particle is likely to be found. The classical world you experience every single day, the chair you're sitting in, the screen you're watching, is really just the smeared-out, macro-scale illusion of these bizarre quantum rules. It leaves us with a profound question. If everything you are is secretly governed by waves of probability, what does that actually say about the nature of reality itself? Thanks for joining The Explainer. We'll see you next time.